Welcome back, students. Welcome to the chapter Chemical Bonding and Molecular Structure. This is part 2 of the chapter for class 11. So in this part we are going to see Kössel-Lewis approach. So this is the first theory that tried to explain the stability of atoms and molecules. And Kössel-Lewis approach is based on the valence electrons of the representative elements. So their theory or their approach is based on the valence electrons of the representative elements, and we have seen about the valence electrons in the previous chapter, that is periodic classification of elements. So what is the valence electrons for a representative? So first of all, which are the groups that belongs to representative elements? They are the S block and P block elements. So S block means first two groups, and the P block means 13 to 18, group 13 to 18. How to calculate the valence electrons? In the case of S block, for the first two groups, it is their group number. So first group has one valence electron and second group has two valence electrons. For P block, what you have to do is take the group number and subtract 10 from it. So 13 minus 10, which means that group 13 has, or boron family, has 3 electrons. Group 14, that is carbon family, 14 minus 10 has 4 electrons. Similarly, and so on, we have 15 5 electrons, 16 6 electrons, 17 7 electron, and for noble gases we have 8 electrons. So what is the formula that we studied? It is nothing but for group 1 and 2, it is the group number, and for P block, that is from 13 to 18, it is group number minus 10. So if you are applying this, you can calculate the number of valence electrons or electrons in the valence shell for the representative elements. So these valence electrons that is given here are generally called as group valence or common valence. So common valence of halogens is 7, or group valence is 7. Of oxygen family or chalcogens is 6. Of nitrogen family is 5. For noble gases it is 8. So these are the names. Okay, so this is about, so Kössel-Lewis approach is about valence electrons. So we can represent or denote common valence of an atom using Lewis symbol. So we will see that what is meant by a Lewis symbol. So we have the first member of all the representative elements, first member of all the groups from the representative elements. So this is the first member of group 1. Beryllium is the first member of group 2. Then from 13 to 18 we have first members starting from boron, carbon, nitrogen, oxygen, fluorine and neon. And in Lewis symbol, along with the symbol of atom, we have the number of electrons or its common valence, you can say. So lithium, being from the first group, has common valence of 1, so we have 1 dot. From the second group we have beryllium, so we have its common valence is 2, so we have 2 dots. Boron from 13th group has common valence of 3, so we have 3 dot. Carbon from 14th group has 4, so we have 4 dot. Nitrogen 5, oxygen 6, fluorine 7 and neon 8. So you will see very soon the significance of giving these dots. What is the significance of these dots in Kössel-Lewis approach? So what is Lewis symbol? Valence electrons of an atom are denoted as dots. Valence electrons or common valence is denoted as dots around the symbol of the atom. So this is how to represent Lewis symbol of an atom. So Lewis symbol of an atom can be used to represent all the representative elements. Clear? Now the basis of Kössel-Lewis approach, or what they have noted, is that Noble gases has a common valence of 8. Noble gases has a common valence of 8. So number of valence electrons for 18th group noble gases are always 8. So according to Kössel-Lewis, they figured it out and said that, or stated that, stability of noble gases is due to the presence of 8 valence electron, or which in other term you can say it is octet. Octet means it represents 8. So octet is the reason for the stability of noble gases. This is the basis of Kössel-Lewis approach. So for all the representative elements, they observed the common valence and they found that the common valence of noble gas is 8 and the only stable atom is noble gases. So they pointed out that stability of noble gases is due to this octet or the presence of 8 valence electrons. So here comes the next question, or this is also called as completed octet or stable octet. So it is called completed octet or stable octet. Question is, what is the reason for the stability of octet? We have already learned this as the reason for the stability of completely filled orbitals, completely filled, especially in the case of d orbitals. So a similar reason is the answer for this question. What is the reason for the stability of octet? However, we will see that reason in bit more detail. Okay, അപ്പം എന്തുകൊണ്ടാണ് octetന് stability? Why is it that octet is more stable than other electronic configurations? So the straightaway answer is octet provided completely filled valence shell for noble gases. It provided completely filled valence shell. So what is the advantage of completely filled valence shell? It has a symmetry. Octet gives perfect three-dimensional symmetry of arrangement for electrons around the nucleus, like the 8 corners of the cube. So we know what a cube is. It has all its sides are the same length. All its sides are of same length. So let's assume that the nucleus is in the center and all these valence electrons will be like the corners of a cube with the nucleus in the center of the cube. Core electrons will be inside the cube and at the corners of cube you will see the electrons. So electrons will be equally distributed around the nucleus. So what's the advantage of this? So now the balance, the attractive and repulsive force between the electron and nucleus and the repulsive force between the electrons is very well balanced. And Kössel and Lewis thought that it is, or they assumed that this is the reason for the stability of noble gases. So it is the octet that is reason for the stability of noble gases. And why is it, what is the reason for the stability of octet? It is like a three-dimensional symmetrical arrangement of electrons around the nucleus, like the 8 corners of cubes where nucleus occupy the center point of the cube. So once we have this type of an arrangement, so all the forces of attraction is very well balanced. Clear? So the next question, since the noble gases are stable due to octet, so the next question is, then why are the atoms in the periodic table other than noble gases not stable? So if stability of noble gases is due to octet, the other atoms are unstable because they lack octet. So that's the answer. So according to Kössel and Lewis, atoms other than noble gases lack stability because they lack octet. Only noble gases have the octet. So the other atoms, since they lack octet, they are not stable. So again the next question, so how do they attain the stability? How does the unstable atoms in the periodic table attain stability? So they attain stability. In order to attain stability, they also need octet. So all those atoms, unstable atoms, requires octet. So how will they get it? To get the octet, they will combine with other atoms. Okay, so when they combine with other atoms, that combining bond is called chemical bond. So when they combine with other atoms, there is the formation of chemical bond. And atoms, when they combine together, they are called molecules. So combination results in molecules, and inside the molecules we have the bond between the atoms, that is called chemical bond, and the result of chemical bond is the formation of molecules. So far we have seen that the unstable atoms combine to form molecules through chemical bond formation. So let us look into an example how this happens. We have already seen this in the chapter 3, chemical bond formation. So yet again we will see on the basis of Kössel-Lewis approach. So I have sodium atom, and in the sodium atom what I have shown here is its valence electrons. So there are inner electrons for sodium, but I have shown is only the valence electron, that is this 3s1. So inside there is electrons which is equivalent to a configuration of neon atom. What I have shown is only its valence electron, sodium being an first group element, it has only one valence electron, or its common oxidation state is 1. Now if you're looking into chlorine, which is group 17 element, whose common oxidation state is 7, has 7 electrons in its valence shell. So again its inner configuration is that of neon, and its outer shell has a configuration, has valence electrons of 7. Clear? So if you are looking into the Kössel-Lewis approach, both of the atoms does not have octet and they are not stable. Both sodium and chlorine does not have octet and they are not stable. So how to attain this stability? Sodium, if he lose this electron, this s1 electron, he will get an configuration of neon, which is a noble gas, and therefore it will have an octet. So the inner shell has 8 electron, inner shell of sodium has 8 electron. So if he lose this electron, his outer shell will be the inner one, second shell will be the outer shell, then he will have that octet. In the case of chlorine, if he accepts one electron, he will have now 8 electrons. So 2 plus 5, already it has 7. If he accept one more electron, he has that octet. So that's written here, losing electron gives sodium the valence octet. So if he lose this, he will get the octet of neon. On the other side, gaining electron gives chlorine the valence octet. Gaining electron will give chlorine the valence octet. So configuration of argon. So let us see what happens if sodium is losing and chlorine is gaining. Sodium donates electron to chlorine. So in that process, sodium will lose and gain this octet, and chlorine, which takes that electron, will gain octet of argon. So it will also attain the octet. So both will be satisfied. So this is what happens when sodium loses its electron to become a positively charged ion, which is termed as cation. Now upon losing, it gets a positive charge and gets a configuration of neon. Upon gaining electron, chlorine, will become negatively charged ion or anion, and the electronic configuration of chlorine has now become that of argon. So this was exactly explained by Kössel-Lewis. atoms that do not have octet, they will take part in chemical bonding. So what type of bonding is formed here between sodium and chlorine? So between cation of Na and anion of Cl. Na plus and Cl, there is an electrostatic force of attraction or electrostatic bond, which is also called as ionic bond. So chemical bond formed between cation and anion is called electrostatic bond or ionic bond. Clear? So this is what was explained by Kössel-Lewis approach. In the coming slides, we will see further examples. So we are going to see another type of chemical bond formation which we have already seen in the chapter 3. So here we have two chlorine atoms. So this chlorine atom has only 7. Similarly, this chlorine atom to have 7 common valence or valence electrons. So both of them requires 1 electron and both of them are not ready to give away electron. So they will decide to share the pair of electron. So they will decide to share the pair of electrons. So both chlorine atom requires an electron for the valence octet. Both of the chlorine atoms requires that. So as a result, both will share this pair of electron. So you can also show that pair of electron sharing between the chlorine atoms like this with a single line or with a single chemical bond. So neither of them of losing or gaining, but both are gaining. Clear? Both are having now octet. Now if you count the number of electrons for this chlorine atom, 2, 4, 6, 8, because both these electrons being shared is also belongs to this chlorine atom. Similarly, if you are counting the number of electrons for this chlorine atom, they also have that 8 electrons. Clear? In that way, they have completed the octet. Each atom allowed to share an electron pair between each other. Chemical bond formed by sharing of electrons is called covalent bond. The bond formed by sharing of electron is called covalent bond. So let us summarize what Kössel and Lewis has told. So they have summarized in the form of electronic theory of chemical bonding. Kössel and Lewis summarized their theories as electronic theory of chemical bonding, which is also called as octet rule. So octet rule explains all what we have seen until now, the Kössel-Lewis approach. To attain octet in their valence shell, atoms combine with each other in two ways. This is the electronic theory of chemical bonding, or it's an overall summary of the Kössel-Lewis approach. To attain octet in their valence shell, atoms combine with each other in two ways. Either by transfer of valence electrons between the atoms, by transfer of, this is what we saw in the ionic bonding, or by sharing of valence electrons between the atoms, either by transfer or by sharing. So when you transfer it, what you will get is an ionic bond. Chemical bond by transfer of electron is ionic bond, whereas when you share it, what you will get is a covalent bond. So sharing of electrons and a transfer of electrons. So octet rule, or the electronic theory of chemical bonding put forward by KL approach, is about the chemical bond formation. So for that chemical bond formation, they used, or the basis was the octet in the noble gas. So noble gas, they found it to be stable because of its octet. So they theorized that it is the same octet what other atoms want. So in order to attain that octet, they took part in chemical reactions and chemical bonding. So chemical bonding, as a result of that, are of two types, that is ionic bonding and covalent bond. As a result of chemical bond, they form molecules. So we will see yet another example for the ionic bonding. So this time the ionic bonding is between magnesium and chlorine. So as we all know, magnesium has an electronic configuration of 3s2. So it belongs to the second group and it has a common valence of 2. And chlorine, we have already seen, it has a common valence of 7, belonging to the 17th group. So magnesium, if he loses 2 electrons, he can gain that octet of neon, octet similar to neon. So for that he has to lose 2 electrons, whereas chlorine requires only 1. Magnesium has to give away 2 electrons, whereas chlorine requires only 1. So what happens? Magnesium will give away 2 electrons to 2 chlorine atoms. One chlorine atom requires only 1 electron, so magnesium will approach 2 chlorine atoms. So he can give away 1 electron each to both chlorine atoms. So if there is magnesium here, so I will write it down. So if we have magnesium with 2 electrons, extra valence electrons to given away, he will approach chlorine on this side and another chlorine on this side, and he will give 1 electron to this chlorine and the second electron to this chlorine. Clear? Now what happens? Since magnesium has lost 2 electrons, he will become Mg2+. Clear? Whereas chlorine on this side will gain 1 electron and this side will gain 1 electron. Both will become Cl- each. So this is what will happen. Magnesium on losing 2 electron will attain required octet. Chlorine on the other hand, gaining 1 electron will attain the octet. So what happens is magnesium gives 1 electron each to 2 chlorine atoms to form magnesium 2+ and Cl on one side, Cl- on one side and Cl- on the other side, which can be denoted like this, MgCl2 as a molecule. If you're writing as a molecule, you can write it like this, but inside the molecule they will be like this as ions. One cation with 2 positive charge and 2 anions with a negative charge each. Clear? So this charge on the ion, in the case of magnesium it is 2+, and in the case of chlorine it is negative charge, is called electrovalence. So charge carried by each species in a compound that has ionic bond, is called electrovalence. So the charge carried by each species. How many species are there? There are 2 types of species. One is magnesium and the other one is chloride. So magnesium has 2+, so the electrovalence of magnesium is 2+, and the electrovalence of chloride is -1. So the electrovalence of magnesium is +2 and chloride is -1. In order to compensate +2, there are 2 such chlorides. But the electrovalence of chloride is -1. Now let us look into the covalent bond of some more atoms or some more molecules. So here the molecules are homonuclear diatomic molecule. Diatomic means it has only 2 atoms. So in the example which we have already seen, so this is Lewis dot symbol of chlorine and another Lewis dot symbol of chlorine. Both chlorine has 7 electrons. So this is the advantage of Lewis dot symbol. So you can see how many electrons does it have and how many does it require to complete its octet. So according to the Lewis symbol, chlorine has, and when they combine they share a pair of electrons. So they form a molecule which has only 2 atoms. That's why we call it as diatomic. And both the nucleus of the atoms or of the molecules are the same. So we call homonuclear. Homonuclear means both the atoms in the molecule are the same. Both the atoms, that is, both are chlorine nucleus. So it is homonuclear and has only two atoms, diatomic molecule. Chloride, a chlorine molecule. Okay, how it is formed? This we have already seen. Two chlorine will share a pair of electrons between them to form Cl, one bond Cl. This one bond is called single bond. So sharing of one pair of electron results in covalent single bond. Clear? Now let us look into the example of oxygen. Oxygen has only 6 electrons. Similarly, this oxygen also has 6 electrons. How much electron does this oxygen require to complete its octet? It requires 8 in total, so there is a lack of 2 electrons. Same is the case with the oxygen. So it requires 2 electrons. What will they do? They will decide to share 2 electrons from each side. So here in the case of chlorine, they shared only 1 electron. Here they decide to share 2 electrons from one oxygen. So what happens? Let us see. So when they shared a total of 4 electrons. In chlorine it was only 2 electrons. In oxygen there are 4 electrons, or 2 pair of electrons. Each pair is represented by a straight line. So here we have one pair. So it is represented by a single straight line between the nucleus. Similarly, in this case, oxygen, there are 2 pair. So we represent it as 2 bonds, or we call it as, in the case of oxygen molecule, we call it as covalent double bond. So there are 2 covalent bonds between oxygen nuclei. This is called covalent double bond. Yet again, if you are looking into the case of nitrogen, each nitrogen atom has 5 electrons. Each has 5 electrons, which means that each one will require another 3 electrons. Another 3 electron. This will require another 3 electron, and this will require another 3 electron. Clear? So what will they do? They decide to share 3 electrons from each part, making it into a total of 6. You can see here 6 electrons are shared, 3 from this and 3 from this. So how many lines will be drawn in between them? There will be 3 bond lines, or we call it as, in the case of nitrogen molecule, we call it as covalent triple bond. So in the case of chlorine, it is sharing of one pair, which will result in covalent single bond. In the case of oxygen, it is sharing of 2 pair of electron that results in covalent double bond. And in the case of nitrogen molecule, it is sharing of 3 pair of electrons resulting in covalent triple bond. More molecules we will see in the coming part.